Slide. All right, and here we go. How do I first address the students? Do I just say hi, welcome back to science class? Or
Be super hammy with it. Be like Matt Patton game theory. Hello, class. Welcome to science class.
I could do that. Hello, class, and welcome to science class.
Perfect.
Okay. Kids, we're going to learn about stuff today. All right. So, moving on from what we have been going over this past week, learn about evolution, right? And we know so far some most important things that evolution takes a long time to happen. And it happens because there are very, very minute and small changes in a species over hundreds of generations, rather thousands of generations. And this week we've been doing a fun activity. I don't know if you think it's fun or not, but an activity on speciation. Um, and we have already seen before you did this Ed puzzle that there can be directional changes in a species. And so we're going to be looking at those those shifts in population right now. Effects of selection. One is a directional shift. Some of you might have seen this in your activities. This causes a shift towards in one direction, like the band. Right? For example, take this warthog and this cactus. Now, warthogs eat cacti. I would imagine that warthogs would go to try to eat the cacti with the least amount of spines on them, right? Leaving all of the cacti in a desert or area with more spines. So, because the cacti with more spines survived, they would then reproduce more cacti with a similar number of spines. In this scenario, we would see a directional shift in the population of cacti with spines, and we would see more cacti with more spines as time went on because of this feeding relationship. There is a stabilizing shift, which is a shift towards the average, towards the middle. For example, with these butterflies, this could happen if the color for their butterfly wings was a polygenic trait, and if all of the butterflies in this species mated a lot, eventually, they would all blend together and have less and less of the extremes and more of the average phenotype. And finally, a disruptive shift in population causes a shift towards both extremes. This is also a shift that you might have seen in your activity this week, where where the average population would die out and populations of two extremes would emerge from that, and maybe possibly one day, depending on the reason for this disruption, become two new species. Let's take a moment really quick, though, to talk about how natural selection and, well, in this case, kind of artificial selection can be a bad thing. One of you actually asked a question about that in your active reading. You asked which one is better, artificial selection or natural selection. And there's not really an answer for that. There's benefits and cons to both. One of the major cons to artificial selection is, and we're not doing this on purpose, but in a way, we are breeding stronger bacteria. So let's take a group of bacteria, for example. All of those blue dots in the corner are bacteria that are weak against antibiotics. However, that red one has a mutation a random mutation that just happens to make it a little bit stronger against antibiotics. If we use antibiotics on those bacteria, all of the blue ones will die, leaving just the red one. And if the red one is left, then it's going to reproduce, and it will reproduce more bacteria that are also resistant against antibiotics. And now we've essentially, kind of in a way, through artificial selection, but not really, created bacteria that are stronger, making it an issue for us. And that was also an example of a directional shift, right? We have bacteria that are pretty weak, and some bacteria that are stronger. And then after using antibiotics, bacteria that reproduce afterwards are all much stronger to antibacterial products such as antibacterial soap and medicine. All right, speciation. This is what we've been working on all week, is that speciation activity. So this is the process by which a new species is formed. This can occur when a small population of a species becomes isolated from the larger population and then adapts over time to their new environment. In this graphic here, we would pretend that this yellow or a circle symbolizes one species. However, because of some kind of environmental disruption, like this mountain range, and also just like in our activity, they are split into two new groups. And over a long period of time, have so many differences that they become two entirely new species. This requires a barrier to breeding, which means there has to be in order for this to happen, there has to be some reason why the two separate populations can no longer come into contact and breed anymore. It could be a mountain range, like in our scenario that we had. It could be the ocean, a river, it could be a desert. And there's usually a geographic barrier. In our activity, it was a mountain range. And just like in our activity, we used birds as an example, um, right? And so what we found is that we started with an original population that had an average beak size, right? However, over the course of time, because of which beak sizes would be best for getting a certain kind of food, we saw the population start to have a disruptive shift towards both extremes. Um, we got a lot of birds with bigger beaks, which were better for eating tree nuts, and we had a bunch of birds with smaller and longer, thinner beaks, which were better for eating insects, catching and eating insects. There's a little story about, and it's just a story, by the way. Who knows if it's true or not? A story about the coming of man. So they say that people theorize that our ancestors they actually lived in trees. And by the way, they say that our ancestors um, are the same ancestors as apes and monkeys. A lot of people believe that we evolved from apes and monkeys, but in actuality, what we have found now is that there's people and there's apes and monkeys, and then we both had a common ancestor. They say that common ancestor lived in trees. And they say that one day, some small group of those uh, inhabitants that lived in trees fell out of the trees, and they fell into some tall grass. The organisms that fell into the tall grass tend to be hunched over, and the ones that were more hunched over had a harder time surviving. They couldn't see predators coming because of the tall grass, and they couldn't move as quickly. But there were some organisms that stood up a little bit straighter, and those organisms could see over the tall grass. and eventually they would pass on their genes and produce more offspring that stood up a little bit taller. And maybe some of those offspring stood up even taller, even straighter, and they were able to see even more clearly over the grass and had a better chance of seeing predators before they came, and also possibly a better chance of running away. And so eventually over time they say that is how cavemen came to be, and then eventually us. Just a fun story. So, if separated long enough, the two populations will accumulate enough differences in their DNA and physical characteristics that they won't breed together even if the barriers were removed, right? We're not going to breed with monkeys and apes. That'd be the equivalent of what this is talking about. Um, or dogs won't breed with wolves. They can, but they won't. So they're considered to be two different species. At the point where two populations can no longer breed to produce fertile offspring, they are considered two different species. Take this lion and this tiger, for example. Now, a lion and a tiger, they can have a baby, and it's called a liger, and it's real. However, this liger cannot have its own babies. It cannot have children. So that would tell scientists, us, that this lion and this tiger are two different species, because even though they can have a child, that child cannot have children of its own. It is infertile.
What are you drawing?
A liger.
What's a liger?
It's pretty much my favorite animal. It's like a lion and a tiger mixed. Bred for its skills and magic.